Good afternoon, and welcome to today's Machine Design webcast. Our topic today is 5 retaining ring solutions to frequent application design challenges, sponsored by Rotor. I'm Jeff Kearns with Penton Design's Engineering and Sourcing Group. To begin, let me explain how you can participate in today's presentation. First of all, if you're having any technical difficulties during today's session, simply hit F5 to refresh your webcast console. If you need assistance solving common issues, please click on the yellow help icon below the slides. Additionally, we welcome your questions during today's event. We will answer as many questions as possible during the Q&A session that will follow the main presentation, but please feel free to send your questions at any time. To do so, simply type your question into the question window on the side of your screen and hit the Submit button. Also, please be aware that today's session is being recorded and will be available on the Machine Design's website within the next week. You'll be notified by email when the archive is available. Now let me introduce today's speaker. Jay Nasson graduated from Rutgers University School of Engineering with a bachelor's degree in mechanical engineering. He has worked for Rotor and for over 5 years as a technical sales engineer, reviewing prints and coordinating between production customers and customer sales representatives. He is also the lead contact for OEM customers for Rotor, and in his spare time he enjoys cycling and woodworking. Now let me turn things over to our presenter. Jay, the floor is yours.
Thank you, Jeff. As Jeff mentioned, my name is Jay, and I'm a technical sales engineer with Rotor. At Rotor, technical sales engineers assist customers with initial designs, print review, product selection, and pricing. We work closely with OEMs and distributors and help select the correct part for your application. Today, we'll start with a quick overview of Rotor as a company, and we'll review some common design challenges. So Rotor as a company was started in 1957 by Robert Slass. Today it is 100% owned by his 2 sons, Jonathan and Craig Slass, and day-to-day they are both very involved in the company. Craig focuses on the sales side and Jonathan on the engineering side. Rotor has 400 employees worldwide, and that is between our 2 facilities in the U.S. and the Czech Republic and our sales facilities in Europe, in Germany, Great Britain, and also in China. Rotor is a vertically integrated company. This means everything from wire production to engineering, tooling, production of actual parts, heat treatment, packaging, maintenance and service of our equipment and tooling, warehousing, and also our marketing and inside sales and outside sales are all done in-house. This helps us control lead times, which also leads to lower prices and lower minimum order quantities for our customers. On the right side of the screen, there's 4 pictures. The top one is a view of our rolling mills. Below that is a view of our stamping room. Below that, a couple of rings going through the heat treat process. And finally, our shrink-wrapped packages ready to be shipped to our customer. Rotor has 3 main production methods: stamping, coiling, and laser cutting. Stamping is often seen at rings 2 inches and below, and basically is a faster production method than coiling or wire forming. However, you do end up with more scrap. That's why at above 2 inches, we make a quick switch to coiled and wire-formed parts, which will have a slower speed but less scrap, so it ends up with lower prices for us and lower prices for our customers. We also have laser cutting equipment for prototypes and specials. If you have an odd shape that isn't easily tooled, or if you have low quantities that tooling isn't justified for, we can still help you out there. We can also make prototypes, that way you can test a part prior to an investment in tooling or a full production run. Rotor takes quality very seriously. We are ISO TS certified and also recently had our audit for IATF, which will be replacing the TS certification in the coming year. We are also ISO 9001, AS 9100, and ISO 14001 certified. The pictures up top show our quality labs, which include salt spray testing equipment, a hardness tester to the right of that, and a couple of precise measuring devices. The overview of today's presentation is all rings have a function, and choosing the right ring and choosing the proper design will help your application, help your assembly, and help your product function properly. We will now review some common design challenges that may occur when trying to choose the correct ring. The first design challenge that you may come across is rotational speeds. If you have a fast-moving motor or some other fast-moving shaft, you'll need to consider the speeds that you're putting on the ring. This is only a concern with external rings because if you have a ring in a housing, as the speeds increase, the ring just wants to push further and further into that groove. So, picture yourself on a gravitron at a carnival, and you'll see the rings aren't going anywhere. But on the external side, you do have to worry about this. From a design standpoint, a tapered section ring will help to improve radial force, as the RPM limits are directly related to spring force remaining in the ring. The easiest way to picture this is if you take your thumb and your index finger and try to pinch them together, that's the forces you're seeing on a ring, and as you open up, that's kind of the action you see the other way around. Deeper grooves will help you have higher RPM limits, as well as controlling your expansion during installation. The controlled expansion during installation will limit permanent set that gets introduced into the ring and leave as much strength in that ring and spring in that ring as possible. Deeper grooves are better because as the ring starts to separate, the groove wall is still there to keep the ring from being pushed out of the groove. Thicker is not always better for this, as the spring rate is also a product of the aspect ratio. So as your thickness increases, you also need to increase your section to avoid, to ensure that spring force is still remaining in the ring. We have reinforced versions of our rings, which we'll see later in the load section, but basically we have our standard radially installed E-ring, and if you require additional rotation speeds or additional loads, we have our RE style ring, which you actually see pictured on this slide in gold. Likewise, our SH shaft rings have a reinforced version, the SHR rings. Rotoclip can also offer a couple of special solutions for high rotational speeds. Here you see two rings. The top ring is a standard DCR style retaining ring. This is a two-turn spiral ring. They're constant in section all the way around, so they don't always have the highest of RPM limits. But by adding a notch and a punch in the ring, we create a locking feature. On the lower ring, you can see this locking feature, and you can imagine as the speeds start to increase and that ring starts to open, the notch on the top catches on the prong that's sticking into that notch and prevents further expansion. The next design consideration we'll review is operating temperatures and corrosive environments. Basically, picking the best material for your application. Over-engineering is always an issue that you have to consider. There's no reason to go with the most expensive material if carbon steel will work fine for you. So to that end, we'll review some of the materials and give you a general idea of what to look for when selecting a material. So RotorClip offers carbon steels certified to 3 global specifications. We offer SAE, DIN, and JIS specs. They're the same material, but they are triple spec to meet your global requirements. And on those carbon steel parts, you'll see temperature ranges from negative 100 degrees Fahrenheit to up to 600 degrees Fahrenheit. And in a few slides, we'll discuss how that range shrinks as your loads or your environment changes. For stainless rings, we have 15.7, precipitation hardened 15.7 MO. This has good corrosion resistance, high tensile strength, and it can withstand temperatures up to 900 degrees Fahrenheit for a short period of time. This 900 degrees approaches the temperature where the precipitation hardening occurs during heat treat. Above this temperature, precipitants come out of solution, and you'll see a degradation in the performance of your ring. You may even see catastrophic failure of your application. We also offer DIN 1.4122 stainless. Similar temperature ranges, and then I have a note on here. Why are we not using 420 stainless? 420 stainless has a low carbon content, makes it difficult to heat treat. So you often see a lot of failures resulting with questionable heat treat coming out of these parts. Since the DIN 1.4122 and 15.7 perform better, it's just best to avoid 420 altogether. On our stainless steel for flat wire products, we have 302 stainless, 316, and 17.7. 302 has a temperature limit of 400 degrees, same with 316, and 17.7 will get you up to 650 degrees. The key considerations in stainless that gives it the properties that everyone loves are the alloying elements. So there's a bunch other than those listed, but the key alloys that are useful are chromium. Chromium is what makes stainless steel stainless. Chromium forms a surface film of chromium oxide to provide corrosion resistance. This increases scaling resistance at elevated temperatures. The nickel increases ductility. This makes stainless steel easier to form. This also increases high temperature strength and corrosion resistance. This is particularly useful in industrial, marine, and chemical applications. And then finally, molybdenum, which increases corrosion resistance, adds strength at elevated temperatures, and expands the range of passivity for all parts. Moly also counteracts pitting, especially in chloride environments. To round out our standard materials, we're going to talk briefly about beryllium copper and phosphor bronze. These are 2 non-magnetic options that are very good for marine environments, and you'll see performance up to 400 degrees Fahrenheit. So this is a graph that kind of shows what happens at higher temperatures. As the temperature increases, the performance of the ring decreases. So thrust loads are greatly reduced, material strength is reduced, and eventually the parts will fail completely. So if you're pushing the extreme limits of the thrust load of the ring, you usually want to be in the 100 degree Fahrenheit range. You could go 50 degrees below, 50 degrees above as you start increasing towards the that's 400 degrees, 300 degrees area, you start to lose performance, and then at 600 degrees, complete failure usually. So as you increase temperature, if you have a lower load, it's preferable. Likewise for beryllium copper, you'll see similar performance curves, and same for stainless steel. At the other end of the spectrum, you have low temperatures. So around negative 100 degrees Fahrenheit is usually what we call out for most rings. And at this level, impact resistance is greatly diminished. Brittleness sets in, and there's a danger of fracture. We have a few options for alternative materials. A286 is a stainless steel designed for high temperatures. It'll reach up to 1,000 degrees Fahrenheit. Inconel X750 is a NACE-compliant material. It can be designed for high temperature or NACE-compliant depending on the spring temper used. So you can have 700 degrees Fahrenheit for a max and be NACE-compliant, or you can be at 1,000 degrees Fahrenheit for your max and not be NACE-compliant. Inconel 718 is great for corrosive environments, not NACE-compliant, and will withstand temperatures up to 1,300 degrees Fahrenheit. Alloy is NACE-compliant, and 800 degrees Fahrenheit is a good maximum for that one. Hastelloy is a great material for corrosive environments, not so great for high temperatures. 316 stainless and Hastelloy are also great products for seawater exposure, whereas Alloy and Inconel are great for hydrogen sulfide environments. We'll touch a bit more on NACE compliance. NACE is an organization, and NACE document MR0175 deals with sulfide stress corrosion cracking. We won't go too in-depth here, but basically sulfide stress corrosion cracking is a progressive failure type that produces cracking at stress levels that are well below the material tensile strength, so decreased ring performance. All materials have a hardness that's NACE compliant, but some are too low to function as springs. For example, pH 15.7 MO has a maximum of 30 to 32 HRC max. It's not high enough of a hardness to have proper spring characteristics. On the other end of the spectrum, Inconel X750 gets you up to 50 HRC max while still being NACE compliant. And as a general rule, retaining rings like to be in that 40 to 54 range for hardness. So 50 HRC max is wonderful. Quick overview of our material naming convention. What we'll do is have our series SH, as we talked about earlier. A 1.5 inch ring would be size 150, and then we'd add a material code. So SH-150 SS would be the 15.7 stainless version. Won't go too far in depth on this slide, but if you're rewatching this webinar in the future, just know this is how we call out materials. On some of the alternative alloys, the symbol changes depending on the wire type, so the specific abbreviation isn't listed there. Finishes that we can add to our carbon steel include standard phosphates, phosphate and oil, and a heavy phosphate and oil. After that, we get into the hexavalent chromes, which are not RoHS compliant. Salt spray hours of 48 and 96, and then 480 for heavy zinc dichromate with sealer. And this is not a commonly used finish, so we don't see it too much in the real world. Below that, we have our Z3X finish, which is our trivalent chromate zinc plus sealer. This is a RoHS compliant finish and provides 240 hours to red rust. Below that, we have a couple of color-only options, zinc flash, copper flash, and then our standard oil that gives you shelf life protection. Copper flash and the zinc flash are great for camera systems if you need a visual of whether a part has been installed correctly. And finally, on our spiral type rings, we offer oil dip as our standard for carbon steel. We can offer cadmium and zinc phosphate for the military versions. And then on stainless steel, we can offer vibratory deburring, passivation, and electropolishing as more finished treatments than actual finishes that are put onto a ring. We'll now move on to loads. So thrust load capacity is the amount of force a retaining ring will accommodate once installed in a groove. To go further into depth on that, there's two types of loads, static and dynamic. Static is constant. The load does not increase quickly. Picture putting your hand on your desk and slowly leaning onto the desk. That's a static load. Dynamic loads fluctuate quickly. Version of that would be punching your desk. And the way your hand feels after that, you'll see a big difference between static and dynamic and understand why dynamic loads for retaining rings are greatly reduced from the static. So in our catalog, we list three different loads. We list PR, PG, and P'(R). PR is the thrust load for the ring. And this is the thrust load that causes the ring to fail. This is a product of the housing and shaft diameter, the part thickness, shear strength of the material. These are then multiplied by a correction factor dependent on the ring type and divided by a safety factor. The correction factors were determined by actual testing. So an SH ring versus an E ring, or an SH ring versus another type of ring will have different correction factors in the calculation. The values listed in the catalog have those correction factors taken into account. Next, we have PG, the thrust load for the groove. And the calculation is similar, but the groove depth is used instead of the thickness, and the strength of the groove material is used instead of the ring material. You'll see that there's a safety factor of 2 on the groove and a safety factor of 4 on the ring. It's because the loading for the ring is slightly less precise. The groove staying where it is, but an example of a little bit of fluctuation in the ring loading is if your retained part is loading unevenly on the ring. You may get an earlier failure than if you had a precise 360-degree contact. So a little bit of variation, we up the safety factor, and hopefully you never have any troubles. Finally, we have the max load with a maximum radius or maximum chamfer. There's a decreased load in this scenario due to the moment from contact of the retained part. We'll touch on this a little bit more in a few slides. So since PR and PG are a function of the material strength of the ring or groove, these values are affected by material type. The catalog data listed is for carbon steel and for stainless steel. Scaling factors are used for other materials such as beryllium copper and phosphor bronze due to their lower PSI of material. Easiest way to do this without running through formulas is to multiply the catalog listed values by 0.75 for beryllium copper and phosphor bronze. The back of our catalog lists some correction factors for other materials as well. Likewise, the PG value is affected by the shaft or housing material. catalog values assume cold rolled steel with a tensile yield strength of 45,000 psi for harder or softer materials. Scale by dividing by 45,000 psi. So if you have a shaft material that's 90,000 psi, 90,000 over 45,000 equals 2, you can double the listed thrust value for the groove that we have in our catalog. And again, there's some scaling factors in the catalog for that. So this is a better view of the radius and chamfer mechs that I was mentioning earlier. On the left, you'll see a square corner on the retained part that puts the loading of the ring even with the top of the groove. Next to that, you'll see a corner radius where the load on the ring is higher than the groove wall, and same for the chamfer. Correction factors for this are basically take your P prime R, your the value listed in the catalog, and scale it by the actual radius used. Now, if you're paying close attention, you'll notice that this will approach infinity as the radius or the chamfer approaches 0. So basically, the value should either be the calculated value or the value listed for PR and PG in the catalog. If your radius goes pretty close to 0, you can treat your retained part as square corner. If you do have a large radius on your retained part, you can also include a washer in between your retained part and the retaining ring, and you can then treat that as a square corner retained part. Another thing to consider is edge margin. To ensure that PG listed in the catalog is appropriate, the shaft or housing must have enough material to back up the groove wall. When Y, the edge margin, is 3 times, let's start this again. The distance between the groove wall and the edge of the shaft is the edge margin, known as Y as the variable for that. D being the groove depth. If the edge margin is 3 times the groove depth, the groove can withstand the maximum thrust listed in the catalog. If Y over D is less than 3, a scaling factor should be used. This isn't a linear scaling factor. It's actually based on a graph in the back of our catalog. So that's where to refer in that case. Loads are also affected, or another thing to consider when planning for your load is the wall thickness of a hollow shaft or a housing. Just like edge margin, you don't want to be too thin here, or you could easily destroy your shaft or housing. On the right side of the screen, we show a sharp versus crown side on a retaining ring. The stamping process creates a radius and then a sharp from where the material is moved in the stamping process. There is a very slight difference in the thrust capacity, but our general advice here is if your design requires ensuring that the sharp side is always loaded, you should probably reevaluate your design as you are nearing the thrust load limits of the ring. So if you're asking your assembly line to make sure the ring gets installed in the correct orientation, it's best to go back to the drawing board. Dynamic loads, so punching the table. There's 2 types of dynamic loads, sudden loads and impact loads. Sudden loads occur when a surge in thrust load is transmitted to a ring installed tightly in an assembly. So In this scenario, there is no play between the ring and the retained part. The sudden load should not exceed 50% of the allowable static load, PR or PG, whichever is lower, or whichever is the factor. Impact loading occurs when there is play between the retained part and the retaining ring. A safe impact load can be calculated using PR or PG. For PR, the impact load that can be withstand is PR times the thickness of the ring divided by 2, which provides some additional safety. Likewise, for PG, multiply it by the groove depth, and again, divide by 2. If you need reinforcements, we have those for you. So on the left, you see our SH style ring, and next to that, our SHR style ring. SHR style is thicker and has beefier dimensions. These parts, for example, for the 1 3/4 version, SH175, the ring limit will be 12,992, and the SHR175 will withstand 29,435, so more than double. And in this scenario, you actually double the groove strength as well, 6,200 for the SH and 12,400 for the SHR. Through actual testing, we've found correction factors for these numbers as well that can be used for calculating your own values. There's no correction needed for the SH175, so the multiplier is 1. Correction factor for the SHR is 2 for the groove, which explains why the PG value is doubled for the SHR ring. Likewise, on the right, we have our E-ring followed by our RE ring. The E-ring is a radially installed ring. The RE ring is the reinforced version. The RE ring is actually the same thickness as the E-ring, but the beefier sections provide higher RPM limits and also higher thrust loads. So one interesting solution we solved for a customer is, what do you do when the reinforced ring still isn't strong enough? Customer was using a DSR 24, that's a DIN 471 standard heavy ring, and they needed a little more thrust load resistance. So we looked at a DCR, which is a replacement in the spiral family. The DCR 24 has 2 turns. We checked the numbers on a 3rd turn, and we were the same as the DSR. So due to the manufacturing of this part, we were easily able to add a 4th turn and increase the thrust load to where the customer needed it. And since the tooling and design work for this part were essentially non-existent, the price for this part was very similar to the standard part. No tooling cost, no laser cutting cost, which is something we could have done. We could have taken a DSR, made it even thicker with laser production, but it's a more expensive part. Also, the sections, as you make the ring thicker, again, play into the spring force, and the ring may have taken permanent set beyond what is ideal for during installation. Another consideration when designing your applications is clearances. One of the first real-world lessons that engineers learn after graduating from school is that you can use SOLIDWORKS to draw things that cannot be assembled in the real world. Another way that people see this all the time is you buy a couch and you try to get it into your house. It doesn't fit through the door. So now you either have to modify your couch or return it to the store, and no one wants to return a couch. So similarly, when designing your application, you always want to consider clearances when selecting a retaining ring. We have here two of our problem solvers, the HOI and SHI series. These rings are inverted lug versions of the HO and the SH ring, and allow for a little more clearance in your installation and design. And we'll go to the next slides and see these in action. So this is an RE ring that's trying to rotate, or a shaft that's trying to rotate with an RE ring on it, but we're getting some interference from the tabs on the HO ring. So we can move to an HOI version, and you can see we get full rotation. Another version of a similar issue, installing an SH ring in a bore. You can see here the SH ring, just after it fits, doesn't quite fit into the housing. So we can solve that with an SHI ring. Slides easily into the housing. As you design parts, you'll see this more and more, and hopefully one of these parts or one of our other low clearance options will get you out of some trouble one day. Another thing to consider is axial endplay. In the perfect world, tolerances wouldn't exist. If you had a 10 millimeter section of an application, it would be 10 millimeters. This isn't the perfect world. This is the real world, so we have tolerances. Luckily, Rotor Clip has bowed and beveled rings to help you make up for this worst case scenario. Bowed rings are offered in our housing, shaft, and also radially installed versions. They offer resilient take-up by acting as a spring. They can also dampen vibration and oscillation, whereas the VHO and VSH rings act like a wedge, taking up the end play of your assembly. So here's some examples of our bowed rings. You can see how they look when they're installed and get a nice visual of how they would work. Calculating positioning for these involves three key factors. There's the Jmin and Jmax that are found in our catalog. Bmin and Bmax should be known from the design of the retained part, Bmin being the smallest size and Bmax being the largest size once you account for tolerance. The front of the groove should then be calculated to be between Amin and Amax. Amin and Amax being the plane of the location of the front of that groove, always from a plane of reference behind your retained part, not from the front of your retained part. So our catalog lists our Jmin and Jmax values and the overall resilient end play take-up that the ring size can achieve. So on these examples, we're looking at 11 thousandths of take-up. That's 11 thousandths of tolerance that you can have in your retained parts. Beveled rings come into play above 1 inch. Bowed rings are usually below 1 inch. They go up to about 2 inches, and basically above there it makes more sense to switch to the bevel series. VHO and VSH, as I said, are useful above 1 inch, and they're easily compared to select fit ground rings, except they're less expensive, and more versatile. So on a ground ring, you'll take a standard blank and grind to multiple thicknesses, say 2.5 millimeters, 2.48 millimeters, 2.46 millimeters, stepping up and down in small increments. The VHO style ring can take care of that tolerance stack with just one ring. This leads to less inventory for the customer and less cost to the customer, since the bevel can be integrated into the stamping tool or even formed into the wire before wire forming. A couple of general rules for beveled rings. When you locate your groove, you want to make sure that the ring is seated at least halfway into the groove and does not bottom out in the groove. If the ring bottoms out, you can't guarantee that your retained part is tight against the retaining ring. B-min and B-max in this case are known from the design of your retained part, just as with the bowed rings, and U and D are catalog values, U being the thickness of the ring after the bevel, and D being the depth of the groove. At Rotorclip, we always like to give you more, so we're giving you a bonus solution. These are wave springs. They're a great replacement for bellville washers and coil springs. They take up to 50% of the axial space of a coiled ring, or a coiled spring. So if you're trying to make a smaller application, trying to get less head space, wave springs may be the way to go. Likewise, if you're using bellville washers or a bellville stack, switching to a wave spring gives you a single spring option. In a situation where you have 4 bellvilles, you can replace them with one wave spring. You don't have to worry about quality complaints and possible rebuilds if the assembly line only installs 3 bellvilles instead of 4. Also, on our wave springs, we can add shims on the end. Shims can be programmed into the forming machine, so there's no need to add a secondary operation for grinding as you would on a coil spring. Wave springs have an almost infinite number of designs with different dimensions and forces, and once we have a wire size, there's no tooling, as tooling is all matched to the wire. So we make our designs to match the tooling we have, so that we can offer you a low cost and even low volume, if necessary, part without additional costs for tooling. So we have a poll question up right now. I gave you a quick overview of wave springs, and if you're interested in learning more, just click yes. If you're not interested in learning more, click no. We won't be offended. And if enough people click yes, you might see a webinar on wave springs in the future. Probably get to experience that with my coworker Alex. So if you want to meet Alex, click yes. If you're tired of Rotorclip, click yes. We want to talk to you anyway. The final key to any good application is support. Not only does Rotorclip offer retaining rings to support your retained parts and your application, we also offer engineering support. Our website has easily downloadable CAD data, including 3D prints or 3D designs in the installed state. So if you're making an application, go to our website, pull down the ring you need, and just drop it right into your groove. No need to figure out how to design a wave spring or retaining ring in SolidWorks or whatever your CAD program of choice is. We also offer design calculators, PDF prints, and catalogs for all of our parts, free samples, additional online information, and then At our facility, we offer load testing for springs, rapid prototyping with our laser cutting equipment, and 3D printing in our latest 3D printer. We also offer remote and on-site engineering assistance. So if you are looking to have us come visit you, we're usually more than willing to make the trip. Final consideration is packaging. Once you have your design specified, you now have to worry about how to assemble it. And we can offer you parts in bulk if you're looking at low volume, or if you don't mind sorting through parts and picking out the untangling. Because that can be an issue, we offer rings on wire and shrink wrap parts. So rings on wire is an innovation that Rotor Clip came up with that not only provides a easy product for our customer to use, but also provides cost savings because rings are captured off the machine with thin wire through the lug holes and then can be heat treated and finished all together. Allows us more throughput, and also allows us to get simple, easily stacked parts to our customer. If you don't want to deal with the wire, we'll gladly cut the wires and shrink wrap the parts for you. We can also bowl stack or stack many of our parts and put them onto rods, as you'll see second from the right. These rods are easily loaded into our dispensers for use with our screwdriver type applicators. So you can pick a ring, install it, pick another ring, install it. Very easy for you, your assembly people, or the robots that are taking over. And finally, we offer stacked parts not on rod, so they can be easily loaded onto your own automated assembly equipment. So now you know a lot about retaining rings, but maybe you don't know where they're used other than on your specific application. They're all over. They're in sunroofs, side view mirrors, airbags, ignition switches, steering wheels. Skip a few, we'll go to turbochargers, starters, filters, transfer cases, brake systems, transmissions, seating, and door locks. Now that you know about them, you're going to see them everywhere. A couple examples of applications are gear retention, actuators, pulleys, rocker arms, electric motors. We really like that electric motor picture. Quick connects, centrifugal pumps, butterfly valves, side view mirrors, my personal favorite, when you're walking through the parking lot and you knock into someone's mirror and it turns inward instead of just completely breaking off like they used to. The mechanism controlling that is a wave spring in most cases. And then finally slip clutches and fishing reels, and that's just to name a few. So we have a Q&A. Hopefully you've been asking some questions with the Q&A tab during the presentation. And we'll try to get some of these answered now.
Yes, we have already had a few questions, so we're going to get into them right away. If you'd like to ask a question, please just type it into the question window and hit the submit button. We'll hopefully have time for it. The first question is, what is your turnaround time for special or parts that are not in production?
So turnaround time is very dependent on part type. Our laser equipment, we usually offer a lead time of 6 to 8 weeks. We can push that lead time up if necessary. As far as parts that are wire formed, where all tooling is in place, we're again around 6 to 8 weeks. And then if tooling needs to be designed, especially for stamped parts, lead times can extend up to 16 to 20 weeks.
Okay, and I think we have a few questions here. I'm just going to run through. Does RotorClip offer free samples? Are your rings ROHS compliant? And do you meet military standards?
So RotorClip offers free samples of in-stock parts off our website. If you go on our website, you can request, depending on the size, between 2 and 6 retaining rings to test. And we ship those out via standard mail, although if you need them a little bit quicker, you can give us a UPS or FedEx number, and we'll send them out however you like. As far as RoHS compliance, all of our base materials are RoHS compliant. If we add cadmium or zinc dichromate to our rings, we are no longer RoHS compliant, but the majority of the rest of our finishes are RoHS and REACH compliant. RotorClip offers military standard rings for our tapered section rings and our spiral products. We also offer aerospace spec spiral rings as well. The next question I see here is, can your parts be customized if needed? So customization on our wire form parts, our constant section wire form parts, is pretty simple. It's just a matter of changing the material size or changing the diameter. On our tapered section rings, we can often change thickness by a gauge or two. Beyond that, we would need to look into retooling, and that's where our laser machine comes in very handy for low volume samples. See a question here from one of our participants on what is the largest diameter ring you can make / have made. Currently, the largest ring we have made is 945 millimeters. That's almost a diameter, or around 38 inches for those speaking in inches. On the small end, we're talking smaller than a pencil eraser. Those large rings were DIN standard rings. The DIN spec goes up to about 1,000 millimeters, and we cover the entire range. On the inch side, the standard retaining ring specs go up to 15 inches. Do we ever work with titanium? If not, what is the lightest alloy we work with? We have not worked with titanium. The heat treat gives us a little bit of trouble there, but we do often get requests for it, and we are always looking for ways to process titanium for our customers. What is the leading cause of locking tab failures on spiral rings? I have not seen a failure on a locking spiral ring. The leading cause, if I were to think of one, would be if the tab was not punched high enough, so you did not get engagement, or if the ring was not in, if the ring did not have any axial force on it, so the two sections could actually separate, allowing the ring to flip over the tab.
Okay, do you want to give us one more question before we go? We're running out of time.
Sure. Yeah, and if we have any left over after that, we'll try to send a direct answer. See if we have a good one. All right. I have a 3/16 inch diameter pin that I am using as a hinge pin for a small lever. What is the best kind of retaining ring to hold this pin in place? The ring would sit coincident against a flat face. So at 3/16, You may want to try our E-rings or C-rings due to their ease of installation. We also have SHM rings at that size. And I believe we may have SHF style rings at that size. SHFs can be used without a groove, so that would decrease the cost of manufacturing your pins since you wouldn't have to cut a groove. Hope that answers your question, and thanks everyone for coming out today.
All right. Well, that'll conclude our presentation. On behalf of Machine Design, I'd like to thank Rotor for sponsoring today's event, and of course for all of you for joining. Have a great and productive rest of your day.